Hello viewers, good afternoon. Myself Professor T.N. Oja. I am going to present a new video on gaseous state. It contains many important aspects, so it will be useful for the students. The first slide shows introduction. As we all know, some elements occur as gases: argon, neon, krypton, xenon, helium. Some molecular elements also occur as gases: hydrogen, nitrogen, oxygen, ozone, etc. And a large number of compounds are in gaseous phase. So we use a number of measurement techniques such as those related with pressure, temperature, diffusion rates, surface tension, viscosity, thermal conductivity, solubility, adsorption, enthalpy changes, absorption spectrometry, etc., deriving various informations. In the beginning, let us consider some useful equations. We will use these equations later, but at first glance, these are collected here. The first equation is PV equal to nRT, the famous ideal gas equation for n mole of gas. The second is van der Waals equation, P plus n square A upon V square, P minus NB equal to nRT. It contains correction terms, pressure correction term and volume correction term. Third equation is only for pressure correction term. Volume correction term has been ignored. This situation arises when the pressure is very low, volume is very high. Next equation, equation number 4, is the corrected form of equation number 3, rearranged equation 3. Equation 5 is similar to equation 3, with the only difference it is for 1 mole. Equation 6 is equation 5 rearranged. Equation 7 is pressure correction term negligible. And equation 8 is rearranged form of equation 7. Equation 1 is for n mole of an ideal gas. It implies that at a constant temperature, T equal to constant, dT equal to 0, the product of pressure P and volume V for n mole of gas should remain constant, but no gas is truly ideal. Therefore, deviations from ideal behavior are observed. The kind of deviation or departure depends mainly on the nature of the gas chosen for the experiment, and also on the chosen temperature and the range of pressure. When the causes of deviation were analyzed in detail, it emerged that the molecular kinetic theory of gases considers molecules as point masses having no volume of their own. This postulate is erroneous, not correct. Under normal conditions, gas molecules occupy about 0.014% of the total volume of the container vessel. Obviously, gas molecules have somewhat lesser volume available for their movement. This affects the behavior. This affects the observed properties. The second objection is the kinetic theory ignores any attraction or repulsion between the gas molecules. This is also erroneous. Gas molecules also attract and repel each other when they are close. Again, if the measured pressure is considered, it is actually less than the theoretical pressure. Taking into account these considerations, van der Waals, the famous physicist in 1860, developed equation number 2, which contains pressure correction term Pi equal to n square A over V square, where Pi indicates internal pressure and volume correction term NB or N mole of gas in liter per mole unit. The parameter A is pressure correction constant and has units of pressure over number of moles of gas per unit area, that is liter power 6 atmosphere mole power minus 2. The volume correction term symbolized as small b called excluded volume is expressed in liter per mole. The ideal gas equation PV equal to nRT would require that the ratio shown below should be unity. The ratio is PV over PV ideal equivalently PV over nRT equivalently PV molar over RT for 1 mole given as Z, compressibility index or compressibility factor. Accordingly, as required by equation 9, plot between pressure along x-axis in the range low to about 800 atmospheres and compressibility index Z range 0 to 2 along y-axis should be a straight line parallel to the abscissa. In actual experimental data for gases such as helium, argon, hydrogen, nitrogen, oxygen, ammonia, methane, etc. were used for the plots at 0 degrees Celsius, the results were surprisingly changed. These are shown in this diagram. See hydrogen and helium. The graph line is showing Z greater than 1. For other gases, there is a dip, means Z less than 1, and after certain pressure, Z becomes greater than 1. For ideal case, imaginary case, Z is always unity 1. Explanation for causes of deviations. First, at extremely low pressure, all gases behave as near ideal gases, so that the Z value lies close to 1. It means that equation 1 holds good and both pressure correction and volume correction terms approach zero value and the pressure is extremely low. Second, when pressure is not too high, that is at low pressure, when P is proportional to 1 over V, volume V is quite large, so that the volume occupied by the gas molecules may be ignored, means B equal to 0, without inviting serious error, if any. Also, A over V square term, equation 2, will be negligible. Under such conditions, deviations will be negative, Z less than 1, and the dip in the curve will result. It has been given in question 3, 4, 5, and 6. Finally, PV molar less than RT, therefore negative deviation results. So mathematically it has been proved that when the pressure is not very low, not very high, a negative deviation should result. When the pressure is too high, molecules come very close, repulsive forces become appreciable, therefore gas becomes less compressible, means Z is more than 1, hence the volume correction term cannot be ignored, but pressure correction term can be omitted. Again, the equations have been modified accordingly, and finally we find PV molar more than RT, resulting into positive deviation, that is Z greater than 1. For non-polarizable atoms and molecules like helium, hydrogen, PV molar is greater than PV ideal, at all pressures, indicating their negligible compression. As pressure is increased, that goes on increasing for them, because for these species, means helium and hydrogen, excluded volume B as well as reduction in pressure Pi are negligible. This is illustrated in the figure below at 0 degrees Celsius. Now let us discuss effect of temperature on deviation from ideal behavior, that is Boyle temperature, TB, for real gases. This is a very important parameter. We must know how to calculate Boyle temperature and what is its relation with critical temperature and inversion temperature, and what is its relation with van der Waals constants A and B. During the investigation of the effect of temperature on deviation from ideal behavior, it was found that for each gas there exists a temperature at which real gases obey ideal gas laws, that is Boyle's law and Charles' law, over an appreciable range of pressure. For some gases, the Boyle temperature values are given here. For example, helium obeys PV equal to nRT equation at minus 250 degree, hydrogen at minus 164 degrees Celsius. This graph is for nitrogen gas at different temperatures. Boil temperature indicated by the point where all curves meet. Formula for boil temperature calculation: TB equal to A over RB, where A and B are van der Waals constants. R is universal gas constant. For example, for carbon dioxide gas, A is 3.59 unit, B is 0.0427 unit. Hence, we can calculate its boil temperature, which comes out to be 753 degrees Celsius. Van der Waals equation. The derivation of van der Waals equation has been described in the first video on gaseous state of matter. For the benefit of the viewers, it has been reproduced here. The equation is P plus N square A over V square multiplied by V minus NB equal to nRT. As told before, N square A over V square is the pressure correction term, and NB is the mole volume correction term, or N mole. The ideal gas equation PV equal to nRT, derived on the basis of molecular kinetic theory, suffers from two serious limitations mentioned earlier. One, it ignores the volume of molecules, and secondly, it ignores any repulsion or attraction between molecules. So both volume correction and pressure correction have been shown with reference to diagram figure number 3. The first part refers to calculation of excluded volume. Second part refers to calculation of molecular attraction. It has been well explained here. Volume of one rigid sphere molecule of gas equal to 4 by 3 by d by 2q. Volume of exclusion sphere per molecule is equal to 4 pi d cube by 6, means 4 times the volume of molecule. The excluded volume per mole of the gas is equal to Na multiplied by 4 pi d cube over 6, put as small b. It means compressible volume for the N mole of gas is V minus Nb. The excluded volume V has unit of mole per liter. The second serious limitation of molecular kinetic theory of gases is that it ignores intermolecular attractions. The molecules present somewhere in the mist experience no net attraction, on the neighboring molecules because they are being equally pulled towards all angles. However, the molecule which is just about to hit the vessel wall marked G in the figure is being retarded or pulled back due to inward force of attraction by the neighboring molecules. As a result of this act, the observed pressure P0, P observed, is lesser than the theoretical pressure Pt. That is, P theoretical equal to P observed plus correction term Pi. Calculation of Pi. The force of attraction exerted on the molecule, which is just going to strike the wall, is directly proportional to the number of molecules present per unit volume of the bulk sample. This is related to the density of gas rho and inversely proportional to the bulk volume V. Further, the internal pressure Pi is also proportional to the number of molecules per unit volume of gas which are about to strike the wall at any instant. Therefore, we can write Pi proportional to rho square or 1 over V square. It means Pi equal to A over V square. On molar scale, Pi equal to An square over V square. The proportionality constant here depends on the nature of the gas. Its unit can be derived as shown here. It comes out to be dm power 6 atmosphere whole power minus 2. Now we can write van der Waals equation including the pressure correction term and volume correction term as shown here. P plus n square A over V square V minus NB equal to nRT. For ideal gases, A equal to B equal to 0. Here is a table showing A and B parameters for some gases. Summary: illustration of pressure correction term and volume correction term has been summarized here. When the density of the gas is quite high, the pressure correction term can be very small and liable to be ignored. Under such conditions, the equation can be abridged as follows, means PV equal to RT plus PV. For n mole, Vm is molar volume. At moderate pressures, volume correction B can be left. And the equation becomes PV equal to RT minus A over Vm. It means PV less than RT. These considerations help us in understanding the magnitude and direction of deviation from the ideal gas behavior. It may be noted that in addition to van der Waals equation given earlier, other equations have also been derived by some persons, some scientists. They explain various aspects of PVT behavior of gases. However, we have ignored them. If interested students can consult standard textbooks. Relation between the van der Waals parameter A and B with TB. At Boyle temperature, gases obey equation PV equal to nRT. It means we can write as T constant, limit P approaching 0, del PV over del P at constant T equal to 0. Now the van der Waals equation is multiplied by V to get PV equal to nRTV over V minus NB minus n square A over V. Differentiation of this equation with respect to P at constant T gives equation shown below. Del PV over del P at constant T equal to nRT over V minus NB minus nRTV over V minus NB square plus n square A over V square del V by del P at constant T. Here T refers to Boyle temperature. But del V by del T, del P cannot be zero, it is always negative. Therefore, the other parts would combine together to give zero value, as shown by equation number 6. Multiplying the entire equation by V square multiplied by V minus NB whole square, and then rearranging, finally we get TB equal to A over RB. The derivation is a bit lengthy, but very easy, easily understandable, and meaningful also. Critical constant Tc, Pc, and Vc of a gas. The gas can be liquefied by first cooling it to a certain minimum temperature and then applying pressure. For each gas, there exists a certain minimum temperature above which it cannot be liquefied by applying even high pressure. The pressure of gas corresponding to this temperature, the so-called critical temperature Tc, is called critical pressure Pc, and volume occupied by 1 mole of gas held at Tc and Pc is defined as critical volume Vc. For polar gases such as sulfur dioxide and ammonia, liquefaction is rather easy, but for the so-called permanent gases like helium, argon, oxygen, nitrogen, etc., critical temperatures are much low. Some data given below illustrate this point. Helium 5.2 Kelvin, neon 44.4 Kelvin, argon 150.7 Kelvin, xenon 289.7 Kelvin, hydrogen 33 Kelvin, nitrogen 126 Kelvin, like that. Sulfur dioxide, being highly polar, can be liquefied simply by cooling to about -8 degrees Celsius at 1 atmosphere pressure. This is very rare example. All gases must be brought down to critical temperature and then pressed by applying high pressure. The critical parameters of a gas are related to van der Waals equation, van der Waals constants A and B. For example, Tc equal to 8A over 27 Rb, Pc equal to A over 27B square, Vc equal to 3B. These can be derived. We have not attempted derivation. We have directly given the values, the relationships, but these can be derived. The normal boiling point of a liquid is approximately 2/3 of Tc. For example, for an hexane which boils at 68.9 degrees Celsius, the critical temperature is estimated as 3 by 2 Tb equal to 512.85 Kelvin. Near satisfactory result. Suppose for a certain gas Pc is 100 atmosphere and its B value is 50 cubic centimeter per mole, then we can calculate its critical volume and critical temperature as follows. Critical volume Vc equal to 3 times B, temperature, critical temperature equal to 8A upon 27 Rb. Such numericals are very important, very simple, very small, often asked in examinations. Similarly, if A and B values for a gas are given, then Vc, Pc and Tc can be calculated. An example has been shown here. Alternatively, if critical constant for a gas are given, its A and B can be calculated using similar relationships. These various relationships are easy to remember, but they require practice. Reduced parameters of a gas. For a gas, the ratio P over Pc is called PR. reduced pressure. V over Vc is called VR, reduced volume. T over Tc is called TR, reduced temperature. A generalization called the law of corresponding states says that if two or more gases have the same TR and same PR, their VR will be matching, same. Next, we discuss a very important parameter, inversion temperature. In thermodynamics and cryogenics, a temperature called inversion temperature, TI, which is characteristic for each substance, is very important. In fact, TI refers to a critical temperature different from PC, below which a gas gets cooled during adiabatic expansion under conditions of constant enthalpy, means delta H equal to 0. Above Ti, it gets heated up. Relation between Ti and Tc. Critical temperature Tc equal to 8A over 27 Rb. Inversion temperature Ti equal to 2A over Rb. Comparing these, we get inversion temperature Ti equal to 27 by 4 Tc. The maximum inversion temperature for helium is 24 K, and that for hydrogen is about 2 to 4.7 K. So the temperature of H2 and helium will not fall at ambient temperature during Joule-Thomson isothermic experiment. Instead, they will get warmed up, heated up. This is a strange behavior. For nitrogen, Ti equal to 621 Kelvin, and for oxygen, its value is 764 Kelvin. Joule-Thomson coefficient mu Gt is 0 at inversion temperature. And also note that mu Gt equal to 2A over RTI. It is positive as long as 2A over RT is greater than B, and negative when the symbol is reversed, that is less than B. Numerical has been solved here. For hydrogen gas, control constant A and B are given. We can calculate temperature inversion using the formula Ti equal to 2A upon Rb. Some questions have been included here for the benefit of the viewers. Most of the answers of these questions are given in this video and in a previous video. At some points, hints are also provided. So, for revision purpose, the students should go through these questions, try to answer them, try to remember various relations. They will benefit from this. This slide also shows those questions continued. In third slide also, the questions are continued. Humble lines for you, people, for your benefit. While revising this topic, note down all important equations along with the units of various parameters. Also try to draw different PVT graphs and explain their significance. Solve different numerical problems given in the textbooks. Make a summary note of definitions of important terms. Keep in mind that no ideal gas exists. All gases are real or imperfect. Under the conditions of very low pressure, their behavior may be considered as ideal, near ideal. Try to make computer simulations of molecular motions, collisions, exploded volume, and isotherms. Do self-evaluation regularly. Success does not come on its own. It is achieved through dedication and practice. So do not fail in doing practice. Here comes the end of this video. Thank you very much for watching this video. Please do like and subscribe to my channel. Thank you very much. I am Professor Trivi Narayan Oja, retired professor. Thank you once again.